Um, so yes.
I think I'm in the wrong class.
Oh,
So 314.
no. Yeah.
Did they move it?
Well, it would have moved last week. Do you know who your professor is?
Oh,
Shirley, yeah. Let's pause for one moment and I can help you out there. So we left off, we were talking about multiplying and dividing fractions. You may recall multiplying fractions is really straightforward compared to having to add or subtract them. The big thing is that you don't need a common denominator when you're multiplying or dividing fractions. You can just go right into it. However, you will need one for the case where you are adding or subtracting fractions. So let's see why. The sum or difference, so either from adding or subtracting two rational numbers, remember a rational number is kind of like a fraction. If they have the same denominator, all you do, if you're adding them, you add their numerators together into the new numerator, and then the solution here will have that common denominator, whatever it was. Same idea with subtraction. So you don't subtract or add their denominators. You keep whatever that common denominator is, and that's going to be the denominator in your answer. You simply add or subtract the numerators, the top numbers of the fractions. And so if that is the special case where you are already supplied two fractions that have the same denominator, it's really straightforward to add or subtract them. What we're going to end up having to do in most cases is get a common denominator. That is going to be our goal. So let's look at a couple examples of this. Let's say you want to look in at 3/7 plus 2/7, 3/7 plus 2/7. Well, hey, today's your lucky day. They already have the same denominator. As you can see here, they both have a denominator of 7. Great. The answer is going to have a denominator of 7, at least initially, then you might simplify later. But for the moment, I can add those fractions together. So since they both started with a denominator of 7, they're going to end up with a denominator of 7. And then I just add their numerators, their top numbers together in this case. So 3 plus 2 is 5, and you end up with 5/7. Pretty straightforward, and let's look at the next case. 11/12 minus 5/12. Well, they already both have the same denominator of 12. So when we do the subtraction, the answer is also going to have a denominator of 12, at least initially. So 11/12 minus 5/12 becomes just 11 minus 5 on top, all that over 12. 11 minus 5 is 6, so you end up with 6/12. 6/12. However, you can ultimately reduce 6/12 to 1/2. You would have, if you wrote them kind of in factored form like that, you'd have something like that. And so you end up with 1/2. So you're going to start off with the same denominator in your answer initially. Then if there's any simplification that can be done, you go ahead and you do it. Finally, we've got -5 1/4 minus -2 3/4. Well, the couple things you'll notice, first of all, you're subtracting a negative number. What that's going to do is those negatives are going to basically cancel each other out, and it's going to become addition. So you're going to have addition here in just a moment. But the first thing we need to do is we need to deal with each of these mixed numbers. We will want to convert them into fractions that are improper, that have a denominator that is smaller than the numerator. So zooming in on -5 1/4, you would do 5 times 4, which is 20. Add 1 to it, you'd have 21 over 4. And that's what they get here, and then they just maintain the negative sign they already had. Two and 3/4, you do 4 times 2, which is 8. 8 plus 3 is 11, so you'll end up with 11 over 4. And now we're doing -21 over 4 minus -11 over 4. Minus a minus is going to turn into addition, as per our rules of addition, subtraction, and all that. So you're going to end up with -21 over 4 plus 11 over 4. They have the same denominator now, which is good to see. So the answer is going to have that same common denominator. You don't add their denominators. That's not how that works. And you're going to end up with -21 plus 11 on top. -21 plus 11 is going to be -10. So you'll have -10 over 4, which reduces to -5 over 2. -5 over 2 in that answer. Any questions on that? Pretty straightforward. How many of you like it when they have the same denominator? How many of you are like, yeah, that's what I want to see? Yeah, that'd be great. But there's very few things we like that ever come to fruition, that ever actually happen. So while we may love it when they have the same denominator, how many of you think you're going to see that a lot? Probably not. Now, again, this is where the beauty of multiplication of fraction lies. It doesn't matter if they have the same denominator. You can multiply straight up. Addition, subtraction, not so much. So we need to talk about adding and subtracting rational numbers that have different denominators, that don't have the same denominator already. The long and short of it is you're going to have to get the same denominator. You're going to have to get both fractions to have the same denominator. And so we're going to get the same denominator by finding the least common denominator, aka the LCD. Lots of stupid abbreviations to memorize. I don't like all these abbreviations. We've had LCD, but we also had the GCD, the greatest common divisor, which is not related to this. We also had the LCM, the least common multiple, which actually is exactly what we're looking for here. The least common denominator is just the least common multiple of your denominators, which again is super confusing to have to talk about it like that. It's annoying that we have to talk about it like that. But I'm going to make this explicit. Oh, we need a darker color. How about red? The least common denominator, or LCD, is just the least common multiple, or LCM, of your denominators. Which is a bit annoying. I'll give you that. I will admit to that. It's a bit annoying for the simple fact that now that's just more terms and definitions and stuff that you have floating around. But it is the truth. It is exactly what we're looking for here. No way to avoid that. Let's look at a couple examples of that. Let's work that together. And you know what? Let's just jump in. Let's just jump in. Let's say you wanted to do 3/4, 3/4 plus 7/10. Look at their denominators, 4 and 10. Are those the same? Is 4 equal to 10? Not on this planet, not on any planet that I want to go to, and I probably couldn't reach that planet if I believed that 4 and 10 were the same thing. You need a lot of math to travel through space. So no, these are not the same denominators, so we can't add them straight up as they're written. What we need the LCD. We need the least common multiple of the denominators. So list those bad boys out. What do you got? What do you got? What do you got? You got 4 and you've got 10.
You got 40.
40 will work, yes. So you're on a great idea here. 40 is a common denominator. Yeah, and it will work. And to be honest, if your intuition tells you to do 40 real quick, to just multiply the two denominators together, and you can make it work out. And then you simplify your final answer. Little Kansas in the morning. It's okay. Computers and technology are evil. Trust me, because I am one. I'm a living, talking cyborg. That's not true at all. Please don't tell people that I said that. I mean, you can tell them I said it. Just don't tell them that I really think that about myself, because I don't. Anyways, so what we were saying, if you're comfortable doing 40, you know how to do it, you do it right, and you simplify your final answer, you're going to get the same final answer as long as your process was correct. So in that case, you may not want to fix what ain't broke. But in this case, there may be, what we're looking for is the least common denominator. Is there a number smaller than 40, which is a multiple of both 4 and 10? And we're going to see there is. And in general, you're going to want to go with that one because it's going to end up giving you the least hardship or the least amount of difficulty in the long run. So we can find the LCM using our little trick of doing prime factorization. But if the numbers aren't too big, you can just list out the multiples and probably be okay. And you know, the multiples keep going, 28, 32, 36, 40. Let's see if 10, oh, there we go. We found it, 20. We found the least common multiple. There's nothing smaller than 20, which is a multiple of both 4 and 10. Okay, so now we know the least common denominator. Let's move everything up. Now we know that the least common denominator is going to be 20, but here's what we have to do. We need to re-express both of these as fractions that have a denominator of 20. But I can't just change the 4 to a 20 and go frolicking in the fields. That's not how that works. If I'm going to change the denominator, I also have to change the what? Numerator. That's exactly right. You need to compensate because 3/4 is a very specific number. If I only change the denominator, I'm changing the number itself. But if I change them both at an equal rate, I'm actually keeping the same number. So here's what we're going to do. What would 4 need to get multiplied by to get it up to 20? 5. So I'm going to multiply the bottom by 5. So what do I also need to do? Exactly. Multiply both the top and bottom by 5. And only on this fraction. We'll adjust this fraction separately. Let's do it right now. What does 10 need to get multiplied by to get to 20? A 2. So what do I need to do to the top? Exactly. Do it to both of them. And so now you're going to get 15/20 here. What are you going to get for the second fraction? Very good. But they have the same denominator. That is the whole point of this song and dance. And so now we do 15 plus 14 on top. On bottom is that same 20. We don't add the 20s. What's 15 plus 14? Looks like it'll be 29. Does it look like 29/20 can be simplified? 29 is a prime number. So I'm going to say it's actually good to go. Ding, and you're done. So we added 3/4 plus 7 over 10, and we got 29 over 20. That's just how math works sometimes. Very good, very good. So now we know the basics behind it. Here they're doing 3/4 plus 1 over 6. We're going to need to do a couple more examples than just that one because the numbers can get gnarly pretty quickly. But you notice that 3/4 and 1/6, they do not have the same denominator. You can figure out what their least common multiple of their denominators is, which will be 12. And so to get 3/4 into a denominator of 12, you got to multiply the top and bottom by 3. To get 1/6 into a denominator of 12, you got to multiply the top and bottom by 2. So you'll end up with 9/12 plus 2 over 12. You keep the 12 denominator, you add 9 and 2, which is 11, and then 11 over 12 doesn't simplify. So you're good to go. Let's try another example. The same idea. So again, the principle is you can't add or subtract fractions that have different denominators. That doesn't mean you can't do anything. It means you got to roll up your sleeves, you got a little work to do, you got to massage them just right, and then you can do it. So let me think of an interesting one. Yeah, there's several we could think of. How about negative 16 over 30 minus 7 over 100? So the numbers are a little bit larger. Should that scare you? Well, I don't think it should. I think it shouldn't be too big a deal, I think. Do they have the same denominator? Not at all. So what do we got to do? Exactly. We got to find the smallest multiple of both 30 and 100. Now here's the skinny. You can use any common denominator technically, and you won't be wrong. You might just be doing a little bit, the numbers might blow up a lot quicker than you want them to and get a little nastier. And we'd like to avoid the nasty numbers, right? You'd like them to be a little bit smaller, more manageable. So could I just multiply 30 by 100, which is 3,000, not Andre, and that would be a perfectly usable denominator. 3,000, would that work? It would work. It would work. I can multiply the top and bottom of the 16 over 30. I can multiply it by 100. I could go to the other one. I can multiply the top and bottom by 30. I'd get that 3,000 denominator and I'd be good to go. But the numbers are going to get a bit nasty, aren't they? Yeah, they're going to get a bit large. Also, that means when you get to, after you've done the addition or subtraction and you come down now to simplify, well, you're going to have a harder time simplifying because the numbers are larger. It's going to be harder to see trends. You want the least common. Now, how many of you can see what the least common denominator must be? 300, exactly. Yeah, it's got to be 300. Why? Well, again, if you think about the multiples of 30, you're going to have to go out a bit, but it's 30, 60, 90, 120, 150, keep adding 30, 180, 210, 240, 270, but finally 300. You see that 300, and then you think about the multiples of 100, you got 100, 200, 300. So maybe you can see in your head that you're going to end up with 300. I will tell you that is the answer, and I will say this is one you can explore on your own to see why. But the LCD is 300. Try listing out the multiples on your own. Now 30, you're going to have to go out for a while, but it will eventually get you something. So the LCD is going to be 300. Let's give myself a little more space. Now, in the first fraction, you've got 30 as your denominator. What do you need to multiply 30 by to get it to 300? 10. So I'm going to multiply the top and bottom by 10. 10's pretty easy to multiply with. The 100, what do I need to multiply the top and bottom by? 3. Yeah. I do it separately before I try to mix the fractions together. Bada bing, bada boom. 16 times 10 will be what? 160. Yeah, multiplying by 10 is super cool. You're going to get the 300 you so desire on bottom. 7 times 3 is what? 21. Very good. 100 times 3 is still 300. And now you've got the same denominator. Your answer, at least initially, will have that same denominator. And you're doing negative 160 minus 21, which will give you what? Very good. Negative 181 over 300. And now that one's a little tough to decide if that one can be simplified further. You'd have to really think about the possible factors of 181. I want to say 181 is actually a prime number. Don't quote me on that. But it looks like it's not going to have any factors or anything that could cross out or simplify with 300. So I'm going to go ahead and say negative 181 over 300. That's the answer. So 30 and 100, those kinds of denominators are probably about as bad as it would get. Because remember, you can't do any of the first half of this course, the 0332 portion. You can't use a calculator. Thus, the numbers on the exams, while they won't necessarily say they'll all be 2s and 3s, they can't be ultra complex either. They can't be massive or anything. So I think that's about the limit of what you'd be expected to do without a calculator. Any questions on that one? Questions? How are we doing out there in the Zoomosphere? Is everyone doing good? We having a good day? Maybe avoid the rain a little bit. I can understand that. Okay, so we can talk about something. We won't touch too horribly much on this. We have a property of rational numbers. We have a property of rational numbers called density. In fact, there's also the density property of real numbers, which is more famous. All density means is that no matter what, if you give me two different real numbers, or in this case, rational numbers, if you have two different rational numbers, so you can't use the same number twice, if you have different ones, there is an infinite amount of numbers in between those two you started with. What? That's pretty cool, isn't it? How many of you think that's pretty cool? How many of you are just kind of happy to be here this morning? It's raining outside. You were driving a little bit careful. Hopefully you're driving carefully in the rain. I certainly was. How many of you are just, you're space cadets? You're just happy and you're smiling and it's a good day. I think it's a good day. It's Wednesday. Madison says, me. Yes. Very good to hear, Madison. It's just a nice day. There's no reason to freak out about things. But I think, of course, I'm a math person, but I think it's pretty cool that if you take any two numbers, there's an infinite amount of numbers tucked away in between them. That's wild to me. What are the implications of that? Well, it gets a little mathy, but the idea is that you have a choice of as many different numbers as you want out there. Just like you can go all the way, you can think of the numbers 1, 2, 3, 4, 5, 6, 7, 8. They go on to infinity, don't they? Likewise, just between the numbers 1 and 2, there's an infinite amount of numbers you can pick in there. 1.1, 1.2, 1.3. But you can go out to more decimal points. You can go 1.228, 1.229, 1.2291, 1.22946, blah, blah, blah. You can have an infinite number of choices. What does that mean practically for us? Probably not a whole lot, to be completely honest. But it's just a cool little math fact at the moment. So what they do is they say, Oh, well, you can always find a number that's between 1/2 and 3/4 in this case. And what you do is you take the average. So let's work this together. Find a number between 1/2 and 3/4. Well, I promise you, there's actually an infinite amount of them. There's actually an infinite amount of numbers between 1/2 and 3/4. So actually, there's a lot of things I could choose. If I looked at the decimal forms of 1/2 and 3/4, which is 0.5 and 0.75, you could very quickly say 0.6 or 0.7 or 0.51 or something like that. You can find a lot. So let's just use the number that is halfway in between them by finding their average. In other words, we're going to take the average of them. To find the average of two numbers, add the 2, and divide by 2. So I need to do 1/2 plus 3/4 Well, they don't have the same denominator. Perhaps you can see that the least common multiple will be 4. So I have to adjust the first fraction. The second fraction does not need to be adjusted. So you're going to get 5/4 whenever you add them. And now divide by 2 or multiply by 1/2. That's the same as dividing by 2. So you can do 5/4 divided by 2, which will be the same as 5/4 times 1/2, because 2 can be written as 2/1. So we're simply multiplying by the reciprocal. Oops, that's not what I meant to do. And we get 5/8. So 5/8 is tucked away perfectly halfway in between 1/2 and 3/4. Again, why do we care about the density property? At the moment, we just, honestly, it's not something that's uber interesting. It's just kind of a cool little math fact at the moment. There are huge implications if you go deeper down the rabbit hole with mathematics, but for the time being, it's just not that big a concern to us. Now, what you'll see on your online homework, how many of you already gotten into MyLabs Plus? You've already started working on it, very good. You're gonna wanna really get in there and ply away at it. New assignments are being added as we speak here and there. Basically, what happens is in MyLabs, you're going to see a bunch of different homework sections that are all about fractions. And so it's going to just be material we're covering right now in this PowerPoint. And so it kind of breaks down fractions into, okay, here's adding and subtracting them, multiplying, dividing them. Here's getting common denominators. So you might see it broken down a little more granular like that. But ultimately, it's just over stuff we're covering here. We're covering in math. Okay, so a common application of rational numbers / fractions involves preparing food for a different number of servings than what the recipe gives. So if you've ever baked something and it said, oh, well, this is for 3 people and you want to make it for 5 people. And then whenever I make food, I always double that because I like having leftovers. I'm going to go through the effort of making all this food. It's not that much harder to make twice as much. And then I'm going to have some leftovers, and my leftovers, they're going to be delicious. You put them in the fridge, put them in the microwave the next day. My girlfriend makes fun of me because I'll eat cold food. I'll eat cold pizza. I'll eat cold spaghetti. And she's like, you're a monster. There's something wrong with you. And I said, it's just, how many of you like eating cold food? Maybe you are okay with it. Depends on what it is. I agree. Certainly cold soup probably isn't going to be very good, you know. But anyways, so the amount of each ingredient. So let's not get too horribly caught up in this. A chocolate chip recipe for 5 dozen cookies. So you're making 5 dozen cookies with 3/4 of a cup of sugar. That doesn't sound right. It sounds like you need a lot more. I mean, 5 dozen cookies, that's 60 cookies. So maybe these are low sugar cookies, or you've got other flavorings you're putting in there. But anyways, a chocolate chip recipe for 5 dozen cookies requires 3/4 a cup of sugar. If you want to make 8 dozen cookies, how much sugar is needed? So here's the skinny. You want to make more than the 5 dozen cookies that the recipe is calling for. You want to make 8. Well, for every 5 dozen you make, you need 3/4 a cup of sugar. So what you could do is you could figure out how many cups you need per 1 dozen and then multiply that by 8. But doing it this way is actually going to achieve the same thing. This 8 over 5 allows you to scale the amount of sugar you need. If I multiply by 8/5, I'm expanding the amount of sugar I need to cover 8 dozen cookies. And I multiply by the 3/4, you end up with 6/5 or 1 1/5 cups of sugar. How do you measure out 1/5 of a cup of sugar? Well, you're just going to kind of have to eyeball it because 1/5 is not a common measurement. But there you go. Okay, so that covers our section on fractions. Give me just a moment to pull up our next section, which is perhaps more interesting, depending on how you look at things. Perhaps more interesting. Give me one moment, something's not clicking correctly. I blame it on whichever political party I don't like. But I'll never say what that is. I don't reveal that information about myself to anyone. Well, I mean, other than like my friends and my family and stuff, but not to, not to my students, because this is a math class. My opinions on political matters and other such matters are irrelevant to your learning, and I certainly don't want to influence you. I had a teacher in high school when I was a senior. They would teach economics one semester and government another semester of the same year. And he straight up told us on day one. He was a football coach, and he told us straight up on day one. He said, "Look, I don't really know anything about economics." So I was like, "Okay, why are you teaching this?" But okay, he was like, "You guys are going to get a world-class education on government." So we said, "All right, that's fine." And it turns out the world-class education on government, he didn't teach us like how many members of the House of Representatives are there, how many U.S. senators are there, certain key dates in the formation of our political system. It was just him giving us his opinion on like the politics of that day and who he hated and who he liked. And I was always like, this isn't going to help me. I got to go take the AP test or whatever they call it. So anyways, that's just me ranting. For some reason, this doesn't want to load, but that's fine. We'll just proceed. Okay. So The next topic we're going to cover is irrational numbers. Now, I kind of promised this yesterday when we started talking about rational numbers. I said, well, there's also something called an irrational number, and it's going to be the opposite of what you think. It's going to be the opposite of a rational number. So the irrational numbers. So let's recall, we'll just do this aside. Recall rational numbers, which can be expressed as one integer divided by another. Rational numbers, when you write out their decimal forms, either terminate, that is, they stop, or if they go on forever, they do so by a repeating pattern. So let's snazz this up a little bit. Look at that. So a rational number does one of those two things when you write it out as a decimal. It's either just going to stop and that's it, 0.5, 0.72. The number 12 stops. There's nothing else to say about 12. It doesn't go on forever. It's just 12. That's a rational number. But if it goes on forever but repeats, 0.333333333333, that's still rational. It can go on forever. That's fine. 0.166666666, which is 1/6, that is still a rational number. What we're going to see then is if you have neither of these cases, if you have a number that goes on forever and does not repeat, it does not repeat a pattern, you're going to find that that is called an irrational number. That is almost the very definition of irrational numbers. So the set of irrational numbers is the set of numbers whose decimal representations are neither terminating nor repeating. For example, a well-known irrational number is pi. So again, we should have had experience with pi before. And I'm going to go on a little bit of a rant here. How many of you know that March 14th is called Pi Day? Because 314, just like pi starts out 3.14. How many of you have seen like a shirt that has like a piece of pie and it says something about math and it's like, oh, I like pie, or I hate. Listen, I'm going to come out here right now and I'm going to say this. I enjoy mathematics. It's obviously something I've studied a lot of. I enjoy comedy. Mathematics and comedy should never mix. They should stay completely separate from each other because there's no such thing as a funny math joke. Okay, math is not funny. Math should never be funny. Don't think about it. And then when you go over to comedy, if you're any comedian who's up there telling math jokes or something like that, no, stop doing it. Don't listen to them. They're not funny. Math humor is not funny. When someone says, I had some pie because it's pie day. No, don't do that. I baked a pecan pie because it's pie day. Don't do that. Math is not funny. Raise your hand if you think math can be funny. Raise your hand if you're only not raising your hand because you think I'm going to get on you for it. No, it's okay to think math is funny, but you're just wrong because it's not funny. There's no such thing as a funny math joke. You will never hear me make a math joke. You will never hear me make a math joke. The reason is that I genuinely believe that math should be something that you do on one level, and comedy is a completely different thing. So they're completely non-overlapping. Don't make math jokes around me, or you will suffer the consequences, which there aren't any. There's no I'm not going to get on you or anything. I'm not going to fail you just because you told me a math joke, but I'll be disappointed. So anyways, pi. Pi is the number 3.141592653589793238462, blah, 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 right? Do you see a repeating pattern there with pi? I sure as heck don't. And guess what? There ain't one. Now you could say, well, Josh, what if the pattern just repeats every 100 digits? And so we have to put more and more digits until we see that pattern. Okay, fair point, but that does not happen. There are mathematical proofs that can prove that pi is irrational. So it's not a repeating decimal, not going to happen, and it just keeps going and going and going. As the wise philosophers Limp Bizkit once said, it keeps rolling, 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 rolling. How many of you even get that reference? Okay, there's a couple. All right. Limp Bizkit was like 5th and 6th grade for me, guys. And you know, I'm playing Tony Hawk's Pro Skater on my N64. It was a blue cartridge, and I'm listening to Limp Bizkit. That was probably the happiest moment of my life. I tried skateboarding when I was in 5th grade. Did I do a good job of it? No, I hurt myself many times. I hurt my knees. I hurt my popularity at school. So the lesson here is don't skateboard unless you can be good at it. So some of the places that we can find irrational numbers. A common place is a square root. So remember, when you take the square root of a number, you are asking for, hey, what can be multiplied to itself to produce this number? What can be multiplied by itself? So let's go over them real quick. You have the common squares. You have 1 squared is 1, 2 squared is 4. Remember, when you square something, when you take it to an exponent of 2, you're multiplying it to itself. So 2 times 2 is 4. But then 3 squared, 3 times 3 is 9. 4 squared, 4 times 4 is 16. 5 squared is 25. You can keep going. 6 squared is 36. 7 squared is 49. 8 squared is 64, and so on. Again, the benefit of learning that 12 by 12 multiplication table is you automatically will know the first 12 squares. You automatically, because they're on that table. So this is, let me write it out. This is the process of squaring. Square rooting goes the opposite direction. Square rooting, now this one won't really give you a whole lot of hope, but now we're going the opposite direction. We're taking the square root of 4. We're asking, what is a number that squared produces 4? What is a number that when multiplies to itself produces 4? Well, we can see from the other column, it's got to be 2. What is a number that when multiplied to itself is 9? What would it be? 3, yeah. So technically, you don't even need that column there on the left, but it certainly doesn't hurt. So square root of 16 is 4. Square root of 25 is 5. Another thing to note is when we do this, when we use this square root symbol, we only want the positive square root. That's why it's called the principal square root symbol. But anyways, if I keep going, square root of 36 would be 6. Square root of 49 would be 7. But now here's an uncomfortable question. How many of you are ready to have an uncomfortable question thrown your way? You ready? You ready? What's the square root of 7? 7 squared is 49, but what's the square root of 7? Well, it has one, but it's not pretty. The square root of 7, what's a number that multiplies to itself to get 7? It's not going to be a nice whole number. It's not going to be 2 or 3. It's going to be actually something in between 2 and 3. So square root of 7 here will be in between 2 and 3. But it's going to be ugly. It's going to be like 2.67489, blah, 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 blah. It's going to be a nasty number. And in almost every case, when you take the square of something that is not already known to have a nice, pretty, cute square root like this, you're going to get a number that's nasty, that goes on forever and ever, and it doesn't repeat. There's no repeating pattern. The reason why? Well, we don't quite go into that. But long story short, If you take the square root of a nice, clean, perfect square number like 36, oh, you get 6 and everything's wonderful. So yeah, they just go through squares there. So the square root of 36 is 6. But let me give you a different square root. I'm going to use a calculator. So here's a little thing. You're not going to be asked to do nasty square roots without a calculator. You might be asked to do the square root of 36 or the square root of 25. That's something you should be able to do. But let's look at the square root. How about the square root of 28? Well, 28 is not a perfect square. 25 is the closest one. Square root of 25 would be 5. But 28 is in between the square root of 25 and the square root of 36. Thus, the square root of 28 is going to be in between 5 and 6. Now, I can't tell you what it is off the top of my head because that is something the calculator needs to do. So I'll bust that out for just a moment. Give me that square root symbol. And you're going to get 5.291502622129181. And here's the skinny. Your calculator says it stops. Your calculator, how come the calculator can't show an infinite number of digits? Well, because that's silly, right? The calculator is a finite thing. So the calculator makes it seem like it stops. You have to understand that it doesn't actually stop. It's going to keep going, and your calculator has to cut it off at some point because it can't display an infinite number of digits. None of us here can look at an infinite number of digits. It's silly. The screen runs out. But the point here is that square root of 28 will just keep rolling without a repeating pattern. And that's because 28 is not a nice, clean, perfect square. So like I said, we've already gone over some of the basics of square roots. Every number has a square root. It just may not be pretty, but every number does have it. It just may be an irrational number. So we actually have a few interesting rules before we go into that. Let's look at the different kinds of numbers again, and let's add another layer to it because we've been already doing that. So let's see. Let's say that this big box here, this big box is your box of rational numbers. Now, we didn't talk about this, but there's a special symbol for rational numbers, and it's kind of hard to draw. I'm going to draw it in the more free space here. It's going to look like a Q, but then it has this weird, funky line on the side of it. So these are the rational numbers. They use that Q. If you're curious, the Q stands for quotient, because it's a quotient of numbers. So it makes sense. So you have your rational numbers wrapped inside that. We talked about this last time, but we're expanding it. Inside your rational numbers, you have the box of integers. And you might recall we used this symbol for it. There's like a weird Z. Give me one moment to check something. The integers, and then even inside that, we had another box that we called the natural numbers. Natural, and we used this symbol for those. There's like a weird N. And so now we'll put a few examples into there. Some natural numbers, you have like 1, you can have 17, you can have 3,468,221. Positive whole numbers. Now, every natural number is also inside the box of integers. So the number 1 is also an integer because it's inside that box too. Now, some integers that are not natural are 0, -4, things like that. So the number 0 is in the integer box, but it's not in the natural number box. But it is in the rational number box. So now some rational numbers, -3/7, 14/901. The rational numbers can be expressed as fractions, but look, anything that's natural is also an integer and is also in the larger box of rationals. So that's a cool fact there. But now we have an entirely new box that we can put in. It's actually technically larger than the rational number box. It's much larger, in fact. But we don't exactly have a concept for that just at the moment. And now we have irrational numbers. That's a completely separate box. They have no overlap with rational numbers because irrational means not rational. The IR at the beginning is negating it. It's saying not that. So you have the irrational numbers, and you have many, many, many examples of those. Pi, we just looked at, was an irrational number, 3.14159, blah, 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 keeps going. Square roots of non-perfect squares, so the square root of 17, the square root of 2 will be in there. There's all kinds of numbers. There's actually a mathematical constant that uses a lowercase e as its symbol. So that's why you usually won't see e as a variable when we get to equations and stuff. But now the rational numbers and the irrational numbers together, the rational numbers and the irrational numbers together form the real numbers. And that's one more term we're learning, real numbers. So altogether, these are the real numbers. There's a special symbol for that as well. And it looks like an R. You may have seen that symbol before. This thing's in the way. There we go. And that's the real numbers. This is a great diagram to memorize. This is a great diagram to know, because this is a breakdown of all the different kinds of numbers that exist out there. Great diagram to know. You will be revisiting this idea, especially if you take future math classes beyond the 2-semester course we're squeezing into 1 semester. If you go beyond this, you're going to be revisiting this idea. I can promise you that. Okay, but back to it. So we have different kinds of numbers. When you see square roots, more often than not, you're going to be working with irrational numbers. And so these things have certain special properties. One of them is if you're taking the square root of something, if you're taking the square root of something and you have a product inside the square root, you have two things being multiplied together inside the square root, you can split those off into two separate square roots that are being multiplied. And vice versa, if you're starting by multiplying one square root by another, you can bring them into the same square root house. You can bring them into the same house together and just say it's the square root of A times B. So the square root of the product is the product of the square roots. Yeah, that's long story short there. Why is this important? It's going to be important in just a moment. It's going to help us to simplify some square roots. And this is true whether the square roots you're dealing with are ultimately irrational or not, whether they come out to being perfect squares or not. It's going to be true either way. So let's see about that. Let's look at square root of 75. Square root of 75. Well, let's think about it. What's another way we can express 75? Well, I could write 75 as 5 times, I think, 15, 5 times 15. Now, that's not on your 12 by 12 table, so I'm just kind of spitballing here. You could rewrite it as 5 times 15. Yes, you could rewrite it, I don't know, as 25 times 3. And I just carry the square root symbol over it. So all I've done is rewritten the inside. But now we've got ourselves a cool warning. You guys are about to be blasted with some cool, all right? Dang, I just promised I would never make like math humor, and I'm getting close to accidentally doing something related to math humor or making a math joke. So I'm gonna have to, you know what? Nope, we're not doing that. See, you always have parents who try to reach out to their younger generations of kids, teachers try to do it too. And they say, hey, skateboarding dudes, you playing on your Tony Hawk game or something? And it's terrible, it's horrible. And that was me borderline getting close to doing something like that. So I'm gonna have to stop myself, pause from doing that. I would never do that. I would never subject you to such horrors. I'm 31 years old. I'm happy to be 31 years old. If you are younger than me, I'm not gonna try and talk about TikToks or something to appeal to you. I'm just gonna appeal to you as, hey, I'm someone who can help you along in your math career. How about we do that? You guys like that? Or do you guys want me to reference TikToks and Vines? Or Vines, do people still watch Vines? Not really. I watch them on YouTube. My girlfriend and I will just watch Vine compilations, and they're great. They're hilarious. But anyways, I'm not going to try to appeal to you on that level because I probably can't, because you're probably just going to see me as some lame man. So I won't do that. Anyways, the reason I rewrote it as 25 times 3 in there, I had a little bit of a deceptive idea behind that, is because now I'm going to apply that rule that says I can split the square roots up and multiply them separately as square root of 25 times the square root of 3. Why would I do that? Why would I do that? Well, is the square root of 3 anything special? No, it's not quite square root of 4, which would be 2. So square root of 3 is nothing special, but it's square root of 25. Exactly. Square root of 25 is just 5. Square root of 3 is nothing. So this becomes 5 times the square root of 3. Now, it's still an ugly number. I didn't make it any less ugly because the square root of 3 is still nasty, and multiplying it by 5 is still going to keep it as a nasty number. But I was able to rewrite square root of 75 as something that's a little bit easier to swallow, 5 times the square root of 3, which ain't so bad. In fact, this is read, you read this as 5 square roots of 3. 5 square roots of 3. And that's going to be a cool little thing we do. In fact, in general, we can simplify square roots in a lot more interesting way. If you find the prime factorization of a number you're square rooting, you can simplify it. You can have a much easier time simplifying it. So let me think of one. Let me put my thinking cap on. Oh, how about let me use a little mathemagic here. $13.50. Let's look at the square root of $13.50. Well, like I said, let's look at the prime factorization of 1350. Now I can immediately see there's a 0 on the end, so 10 and 135. I can do that. 10 can be written as 2 times 5. 135 might be a little bit harder to see, but I can see there's a 5 factor in there. And then 135 is going to be 27, it looks like. 27 can be 3 times 9. Then the 9 finally can be written as 3 times 3 down there, way down there. Let's bring everything up. There we go. Now here's what I'm going to do. I'm going to pair up any prime factors that are repeats. Well, in orange, I see we've got 2 5s here. I also have a couple 3s here. This 2 is all by itself. It doesn't have another 2 to pair up. This 3 is all by itself. It doesn't have another 3 because these 2 are taken. So what I can do, I can rewrite square root of 1350. I can rewrite it as 5 times 5 times 3 times 3 times the leftovers, which is 2 times 3. And anything that's paired up like this, I can branch them off into their own square root houses. Why the heck did I do that? Because 5 times 5 is 25. So I'm doing the square root of 25. 3 times 3 is 9 times the square root of 9. 2 times 3 is 6, so times the square root of 6. But wait a minute. Square root of 25 is 5. Square root of 9 is 3, so it becomes 5 times 3 times the square root of 6. And then 5 times 3 is 15, so it becomes ultimately 15 square roots of 6. So the square root of 1350 might have looked like a large imposing number at the beginning, but it ended up just being 15 square roots of 6, which is a lot easier to digest. It's a lot easier to digest. And prime factorization helped us to do that. It helped us to see what were the pairs that basically could be brought out. Okay, don't go anywhere. I'm going to take attendance and then you can go. I'll let y'all, give y'all another minute to write this down if you need to. Don't go nowhere. If you're in Zoom especially, don't leave.